for this question, you mentioned something of potential energy, and with this Ux. So before we move on to solve this problem, we need to clarify with the definition of potential energy. So what is potential energy? Let's assume there are two objects here, A and B, and A is the host and B is the guest. So this is, let's say B is in A's house. According to A's existence, B possesses some energy. And this energy perhaps will be transferred into thermal energy or kinetic energy or so on. But this energy is just due to A's existence. So this energy will be B's potential energy according to A's existence. And how does potential energy, make effects? Somehow, it is in terms of force. So thereafter, according to A's existence, B experiences a force as well. And the reason is that, according to this existence, some property, perhaps like mass or charge, so B is experiencing an attraction or repulsion according to this property. Actually, this graph is a bit abstract. So how do you understand this concept? Let's say I have a playground. It's quite large, and A is here and B is here. Let's say A is a handsome dude, and B is a girl who's looking for a boyfriend. When A applies some perfume, which is just the favorite perfume of B. So, wow, when B stands here, she might smell nothing about it. But she's looking for a boyfriend. She may hang around over there, but when she's moving nearer to A, well, perhaps over here, she smells something of that perfume. She might think, wow, there might be someone I like with this kind of perfume, but I like that perfume, so I want to go nearer to have a look. Thereafter, B walk nearer again. When she's just walking just in front of A, wow, she may find this is the, a perfect husband or perfect boyfriend for her. So this is a story like potential energy. Let's say here we got this A. A will be the host, and the B will be the guest. And when A applies some perfume, then it has a field. In this field, perhaps everybody in this field can smell the perfume. When B's in this field, she can smell the perfume as well. When she smells this perfume, she has an intention to go nearer. This is like she possesses this potential to go nearer. With this energy, she can move. So that's how potential energy make effects on the objects. Now, let's go back to this question. It asks us to find a point of equilibrium of for the particle, which means the net force is zero. Here we must know the force and the relationship between force and potential energy. Otherwise, we have no idea how to solve this problem. So I have to introduce another concept, that is conservation of energy. These concepts tell us that within the system, if without any external effects, means there's no external effect like absorption of heat or dissipation of heat. So within the system, the total energy will always be the same all the time. So let's say it's just constant all the time. But how to make it into make sense in this question? As long as we know that total energy is constant, means there's nothing changed. But in this question, our potential energy Ux is a function of x, which means when x is changing, the Ux will be changed as well. then sometimes ux increases, sometimes it decreases. So where is those extra energy go? So let's say we got a external, we got a E total, right? Ux is just part. It's not all the time, because sometimes it increases, sometimes decreases. Let's say it decreases to an extent, then what are those extra parts? Well, we know that with this potential energy, look at this graph. When B smells something, she moves. That means, well, in our physics world, when it possesses potential energy, it is experiencing a force exerted by A as well. So this potential energy can be transferred into kinetic energy of this object, right? So which means it's experiencing a force, and this force does work to it. And this work done is just the compensation to this potential energy, and with it all together, they form the E total energy. So I can just write something like U x, right? U delta ux. Perhaps sometimes increases or decrease. We don't know. So I write it as ux1 minus ux2, and this will become the work done. Perhaps it's doing positive work or negative work. We don't know either. But in this case, let's expand this work done into the form that we are familiar with. How to write work done? It's integration of force with the displacement, right? It's from it's x1 minus x2, which means this is the end point and this is start point. So x2 will be here and x1 will be here. And let's make it simpler. In this case, let's say the force is in attraction. So when B goes nearer to A, this attraction force is doing positive work, right? When this force is like a repulsion, it's no longer perfume. Perhaps this girl dislikes durian, so when A is eating durian, B smells it. Wow, it's so awful. I just want to go away. So she walks away. Then this force will be repulsion. But when she's walking away, she's just walking along the force, this repulsion force. So the work down here, if without any external things, it will be just positive according to the potential energy change. So we write this in this form, but let's make it simple. Instead of writing vector form, we just write it into scalar form. It's just from x2 to x1, right? So fx is the force function, and as long as we know that in this case we just our displacement is just on x-axis, so our dr will be dx. So this will be the equation to represent the conservation of energy in this case. But in this question, it's asking for a point of equilibrium. So it's just a point. But how to represent a point, we know that x1 is a point, x2 is another point. So we know that. Let's draw something over here. Let's say x1 is here and x2 is here. When x2 is going nearer and nearer and nearer to x1, but just as long as it touches x1, then it becomes an identical point, right? x1, x2 will be the same. So in this case, we are doing a limitation that x2 is approaching x1. And left hand side is ux1 minus ux2, right? Right hand side, write the same thing, limit x2 to x1. And x2, x1, fx, dx. So when x2 is approaching x1, and in this extreme case, we can say that this delta u will be alright. I still write as delta u because I don't want to move too fast. So delta ux, right? But when x2 is approaching x1, at this extreme case, you can just write x1 over here, right? So it's equal to, and this x2 is nearer and nearer and nearer to x1. So it becomes only x1 to x1, right? dx. And in this case, as long as this delta x means that x1 minus x2 is extremely small, so this delta becomes this delta, right? D, or just in words d. And here, as long as they are almost the same, we can just ignore it. Just fx times dx when it's x1. And we shift this dx onto left-hand side. We got a d over dx with dux, right, equals to fx1. That's what we need for this question. Alright, let's go back to the question now. Let's read the question again. A particle of mass m moves under the influence of a potential energy ux. So we write ux over here. It's a over x plus bx, and m is moving along x-axis, right? It never says anything else, so we just treat it as one-dimensional. And m is here, let's say, where a and b are positive, and particle is restricted to the region of x is greater than 0. Let's say this is 0, so this particle will be only here. It will never be here, right? Just here. Just find a point of equilibrium. So we're going to find a equilibrium point. That is, net force is 0. And just now we got something from our previous part, that is d over dx with ux equals to fx, right? So with this x, we know that the relationship between the force and potential energy. At this point, F equals to 0. So this when x equals to x1, F x1 equals to 0. Then we have d over dx ux, x equals to x1 equals to f x1 equals to 0, right? So we are doing a differentiation for potential energy. We don't need to care anything about this force because it's 0. So we can establish an equation that is d over dx and ax plus bx with x equals to x1, which is 0. So we are doing differentiation now. It's quite simple, a math problem, right? So we are doing differentiation for both parts individually. So it's d over dx, a over x, plus d over dx and bx with x equals to x1. So for this part, a over x, we can just write it into a form of a times x to the power of -1, right? It's doing differentiation for it. And for this part, we know that if we're doing differentiation, we just remain with b. This x goes to nothing, goes to 1. I shouldn't say nothing, it's just 1. So it's b. And here, x equals to x1. And we are doing differentiation now for this part. So we shift this -1 outside and in front of a, right? Times x to the power of -1 minus 1. So it's -2. And plus b equals to 0, right? So we get this equation, and in this case, x equals to x1. So we shift this whole thing into the right-hand side. We got b equals to a times x1 to the power of -2, right? So we got a x1 square. We shift this to left-hand side, and we shift this b to right-hand side. We get a over b. So we got x1 equals to square root of a over b, but plus minus. As long as we know that A1 must be positive, right? Because it's restricted, we think this x is greater than 0. So x greater than 0, ax1 equals to positive a over b. This will be the answer. Actually, for potential energy, I'm going to give you more illustration. Let's say we have a gravitational potential energy, right? In this case, ux equals to negative x g n n. So in this case, gravitational potential energy is just a result of capital M and times lowercase m and g of x. We can just, according to the illustration we mentioned before, this capital M is just like the handsome boy, right? He's applying some perfume, and this lowercase m is just that girl, B. So when A applies some perfume, this m will be, much greater. So this magnitude of this potential energy will be greater. I just mentioned magnitude, so regardless of about the sign. And when this m represents a property of that girl who's loving that brand of perfume, right? If she doesn't like this perfume, well, there's nothing happened. So this m means how much she likes this perfume. If she likes very much, this m will be much greater. Then the potential energy will be much greater. She has much greater intention to move forward and jump into A's embrace. And this x also matters. When x, the distance between A and B is shorter, let's say it's shorter, so the whole thing, the magnitude of potential energy will be greater, right? The distance is shorter. She smells this perfume very well, and she just see this path is very short. She wants to, go forward. If it's too far, perhaps she just gives up. That's the story. And we know also there is another equation named as a electrostatic potential energy. It's in electric world. I also use ux to represent it. It's written in this way. And this q, this capital Q, is just like this n, and this lowercase q is just like this n. And these two things are just constants. You don't need to care about this. And this x are the same thing. So we can use that theory to explain this formula. When this capital Q is greater, or the lowercase q is greater, the potential energy will be greater. When it's shorter in path, then the potential energy will be greater as well. Actually, this m is the mass. Let's say a mass of Earth. This m is the like a mass on the Earth. And in this case, everything is in electrical. So this Q represents a center charge, and this Q stands for a testing charge, such as a nuclear of an atom. And this Q is just like an electron inside the atom. So it's experiencing such force. It possesses this potential energy. And we know that those energy within the system is conservative. If without any external force, external absorption or dissipation of heat. And this is the end of this question. Okay, solved. Hey guys, we're done with the solution. If you have any questions to discuss with me, or you want to share some idea, you can just leave me a message or just comment under the video. Hope you guys like my video. If you like it, please subscribe my channel. See you guys in the next video.